Okay, so in this video we're going to cover section 5.5 in your book, which talks about solving trigonometric equations. And essentially the idea is we're going to do all the same algebra that we know to solve regular linear or quadratic equations, only now we'll have trigonometric functions like sine, cosine, tangent, things like that within the equations. The algebra will still be the same. It just might take an extra step or two at the end because we have a trig function in there. And we'll kind of see that as we work through these. There is one thing to keep in mind as you solve these, and make sure you're reading problems carefully. For the sake of argument, suppose we have the equation sine x equals 1. Pretty straightforward, pretty easy. I want to know all the x's that make that sine equal to 1. And of course, we know our unit circle. So we know x equals pi over 2 is a solution, no big deal. But then if we think about the sine wave, well, yes, this is pi over 2 right here, and that's a solution. But if I keep on going, right here, 5 pi over 2 is also a solution. If I keep on going right here, 9 pi over 2 is also a solution. And it will clearly continue forever this way and that way into the negatives. And so we need a way to kind of list out all of these solutions because there's an infinite number of them. And the way we generally do it is, if we look at this, this is a solution at pi over 2 and 5 pi over 2 and so on. It repeats every 2 pi. So what I can say is my solutions at pi are at pi over 2 plus or minus 2 pi n. And essentially what that means is, for any value of n, 1, 2, 3, negative 1, negative 2, negative 3, I plug that in and I add or subtract it from here. And then that will list out all these all those infinite solutions. And it's just a nice shortcut way that we use to write things out in trigonometry. But sometimes when we're solving problems, we'll explicitly be told to find all solutions, which would mean this infinite solution idea right here. Other times we'll be told find all solutions in the interval 0 to 2 pi, kind of our standard unit circle approach. And generally, 2 pi won't be included. It's closed at 0, open at 2 pi. And then we would just restrict ourselves to 0 to 2 pi, so in this case, x would just equal pi over 2. All the math works out the same, the method of solution is the same. The only difference is, if you're talking about all possible solutions, you need to include this or something like it. It varies for some problems. Or if you're only looking from 0 to 2 pi, just include the normal ones you're used to. So just make sure when reading problems, you know what type of solution you're looking for. So now, let's look at a few problems and solve them out. I have several of these written down that I want to go over. So suppose I have this one. Negative 1 plus sine of x over 2 equals 0. The problem that occurs is, well, x is inside of the sign there, and we have to somehow deal with it. And generally speaking, if we remember from 171, if there's something that causes the problem, in 171 it would be a radical or something like that, an absolute value. You isolate it. So here that causes a problem, isolate it. So add the 1. You get sine of x over 2 equals 1. Now, your book does not actually show this. You can kind of do it yourself in your head, which is what your book's doing, I think. If you want to write it explicitly, how do I get the x out of the sine? I take the sine inverse. So if you want, you can just take the sine inverse of both sides, and you get x equals x over 2 equals sine inverse of 1. And again, your book just uses the unit circle and doesn't explicitly write that step, so you don't have to, but just so we know what's going on. Now, what's the sine inverse of 1? Well, we actually just did that. It's the top of the unit circle. It's pi over 2. But now we want to be careful, like we said, are we looking for all solutions or only the solutions on the interval 0 to 2 pi? We'll do both here so we can kind of practice. If I want all solutions, it occurs at 1 and then it repeats every 2 pi. So I do 1 plus 2 pi n. Now I just have a regular equation. This 2 pi n thing might look weird. Don't worry about it. It's just part of your solution. Solve for x. How do I get x by itself? I multiply by 2. So when I rewrite this, I get x equals, distribute the 2, 2 over 2 cancels and it's pi, plus distribute the 2 right here. 2 times 2 is 4 pi n. And now there's all my solutions. X equals pi plus 4 pi over n. If I want to restrict myself to the interval 0 to 2 pi, which of those angles is in the interval 0 to 2 pi? Clearly it's just pi. So then I would just say x equals pi is my one solution. Good. Pretty straightforward and direct. 2 types of solutions. And like I said, there's lots of ways to do these. So we're just going to look at several of them. Next up. Sine of x minus pi over 3 equals negative root 2 over 2. And there we go. And again, we have the same issue. We have an x inside of our sign there, so we have to get rid of it. So we understand it's already isolated, so all I really have to do is take the sign inverse. But this can look a little bit tricky with the difference inside the parentheses. So one of the things you can do if it looks messy, do a substitution. Let u equal x minus pi over 3. So then I get sine of u equals negative root 2 over 2. And now that's easier. And we know from substitution, I'll just substitute back at the end once the problem is easier to deal with. So if I take the sine inverse, what angle gives me a sine of negative root 2 over 2? Well, let's see. That would be 7 pi over 4. Fourth quadrant, all of you know your unit circle, so that works. But in this case, and one thing to be aware of, when we do the sine inverse, right here, we restrict ourselves. Sine inverse is only defined in the first and fourth quadrants. But are there any other angles that will give me the same sine value? Well, yeah, as it turns out, 5 pi over 4 in the third quadrant will also do the same thing. So in this case, we don't need to restrict ourselves to the solutions from the sine inverse. We're thinking about the unit circle, and we find all possible solutions that will give that value. And both of those u's will. I suppose if we want to continue doing all possible solutions, we will add, let's see, 2 pi in here, and we'll add 2 pi in here. And now, well, since I have everything written out nice and neat, and I've solved for u, now the last step is to substitute back. U is x minus pi over 3, so I get x minus pi over 3 equals 7 pi over 4 plus 2 pi n. Here, x minus pi over 3 equals 5 pi over 4 plus 2 pi over n. And now to get my answer, just add pi over 3 to both sides. And I will get, this is going to be rather messy, so it's x equals 7 pi over 4 plus pi over 3 plus 2 pi over n. Here we get x equals 5 pi over 4 plus pi over 3 plus 2 pi over n. That works completely fine. If you want to kind of simplify it a little, this is not 2 pi over n, I'm sorry, that's a quick typo, it's 2 pi n. If you want to simplify it a little bit, in your homework, a few of you have put on your homework, is this simplified enough or how do you want it? I'm actually okay with that. The most you could do if you wanted to simplify this a little bit more, find the common denominator of 12 and combine those right there. They both have the same common denominator. So if we did that, just to do this one, common denominator of 12, so multiply by 3, So I get 15 pi over 12 plus multiply this one by 4 pi over 12. So I get 19 pi over 12. So I could write 19 pi over 12 plus 2 pi n. And then I'm done. You could do the same thing here. And if you want to simplify it, like I said, that would be fine right there. We don't need to simplify anything more beyond that. As far as solutions only within 0 to 2 pi, well, that's the solution from 0 to 2 pi. And likewise, this is the solution from 0 to 2 pi. Good. Let's see. Oh, we still have time left, so I'll do another video. Another problem before I do another video. Let's see. How about this one? 2 sine squared x plus 7x minus 4 plus 7 sine x minus 4 equals 0. This one is slightly different. I actually have a sine squared in there. But the point here is this looks different, but it's the same. It's what you've already been doing from 171. If I kind of do a simple substitution, and I just let sine x equal, say, u, and then sine squared is u squared, this becomes 2u squared plus 7u minus 4 equals 0. That's just a quadratic, which means this is a quadratic, which means I should be able to solve it like a normal quadratic. Instead of doing u plus something, u minus something, I'll just do sine plus something, sine minus something, or something like that. The principle still applies. So in this case, let's see. Hopefully this will factor. I need two numbers that multiply to 2. The only possibilities are 2. So I'll just do 2 sine x and sine x. And then let's see. I need factors of negative 4 that when I plug them in here will give me a positive 7. Plus 4 minus 1. 2 sine x times sine x is 2 sine x squared. This will give me a negative 4. And then that's negative sine plus 8 sine is positive 7 sine. So there we go. But now, just like the quadratic, set each of them to 0. 2 sine x minus 1 equals 0. Or sine x plus 4 equals 0. For this one, I care about the x, so isolate it. 2 sine x equals 1, and then divide the 2. Sine x equals 1/2. And there we go. Now just find all the angles on the unit circle. We'll restrict ourselves to 0 to 2 pi for these. Find all the angles on the unit circle that give me a sine of 1/2. Oh. Well, that's pi over 6, a 30-degree angle, and 5 pi over 6, 150-degree angle. And there we go. Over here, do the same thing. Subtract the 4, and I get sine x equals negative 4. And now, what angles on the unit circle have a sine of 4, or negative 4? All of you know, and I point this out because I saw it in some of your homework, all of you know sine can only go from negative 1 to positive 1, which means negative 4 doesn't occur anywhere. And this has no solution. You can do that, you can say no solution, do whatever you want. So, these are the only possible solutions. And we're done. I'm going to make another video. As I've said before, YouTube only allows me to make these things about 15 minutes long, and I'm pretty much at my time limit. But I will make another video with a few more problems, just so you guys can see a bunch of these worked out in practice. The key point is, it is the same algebra you did in 171. It's still problem solving. The trig functions cause an issue, so you isolate them. If they're quadratic in nature, you factor them. Nothing changes. The only little one step of difference is at the very end when you do this sine inverse. Not exactly sine inverse, because sine inverse is only defined in certain quadrants. Same with the other inverse functions. But you just find the angles that give you the values you want. So that's the only trig aspect of this.